Okay, so to finish up Euler's method here, we're going to do an example. Let me get a fresh page because this can be kind of long sometimes. So here's the example we're going to do. Find the first three approximations, y1, y2, and y3 using Euler's method. For the differential equation, y prime is equal to 1 plus y with the initial conditions y of 0 is equal to 1. Okay, starting at the ordered pair 0, 1 with that h value, that step size of 0.1. One thing I want to say is that sometimes they don't label this as h, sometimes they label that as dx, that small little step size. So whether it's h or dx, it's the same thing. Okay, so let's just do it. So we already have our first pair, that's 0, 1. So that's going to be our x naught, y naught. To find the next point x1, we take the previous x value and we add to that the step size. So we're going to have x1 to be our next, 0.1 to be our next x value. To find the next y value, so I'm just going to scroll up here. We take the previous y value plus plugging the ordered pair into the function times the step size. So I'll write that all out. It's going to be the previous value plus plugging the previous point into the function, the differential equation, times that step size. All right, so for us, the previous y value was 1 plus, so we'll write this out again. We're just going to be plugging the ordered pair 0, 1 into the differential equation. That's going to be times the step size, which is 0.1. So this f of 0, 1 here means plugging 0, 1 into the right-hand side, 1 plus y. All right, so we still have the 1 out in front. Plugging 0, 1 into here, the 0 is not going to do anything because there's no x's, so we're just going to get 1 plus 1, which is 2, times this 0.1. That comes out to be 1.2. Which means that the next ordered pair is the ordered pair 0.1, 1.2. All right, so that's my x1, y1. All right, so that's the first approximation. Let's find the next two. So then my next approximation, x2, I get by taking the previous x value and adding the step size. So now we're at 0.2. The next y value I get, I'm not going to write the equation again. We'll just write this part. It's taking the previous y value, 1 plus 2, plus plugging the previous point, 0.1, 1.2, into the right-hand side of the differential equation times the step size, 0.1. All right. Plugging this into the differential equation, 0.1, again, is not going to do anything because there's no x values. It's just going to be 1 plus that 1.2. So 2.2 times the step size, 0.1. All right, so just type that in the calculator. I got 1.42 coming out of that. All right, that means that my next point here is the point 0.2, 1.42. One more, because we were asked to do 3. Let's find the third one. The third one we get by taking the previous x value, 0.2, and adding the step size. So now we're at 0.3. The next y value we get by taking the previous y value, 1.42, plus, I'm going to skip this step now. We're plugging the previous point into the differential equation. So really, I'm just going to replace the y with 1.42. So we get 2.42 there, times the step size 0.1. That comes out to be 1.662, which means that my final approximation point is 0.3, 1.662. Okay, so that's all we were asked to do here. We were asked to give these three ordered pairs, the 3 approximations using Euler's method. What I want to do real quick is let me pull up Desmos here. And let's just graph those points that we just got, just to kind of show you what would happen. So I don't know, can Desmos graph points really nicely if I just do that? Yeah, I guess that works. All right, and then my next point was 0.1, 1.2. The next point was 0.2, 1.42. The last point was 0.3, 1.662. Now, of course, we're humans, which means that we only found these 4 points here, but calculators could do what we just did very quickly. So they'd be able to get a whole bunch of points, and I hope you can kind of see that it would be like an exponential function that we end up getting. out of this. So this is curving more and more steeper. More and more steeper, is that a thing? It's curving steeper as we go along the x-axis here. Okay, so that is how your calculator or a computer program would graph out the solution to a differential equation using Euler's method. It doesn't really use Euler's method anymore because there's more advanced ones than Euler's method, which we'll talk about if you get into differential equations, but there we go. There is one other thing that I want to show you guys here, and that's a homework question. I thought this homework question was very interesting, but it is hard if you've never seen anything like it before. So let's do it together. So here's the wording to the question. Write an equivalent first order differential equation and initial condition for the following. And then what they give you is this. Y is -1 plus the integral from 1 to x of t minus y of t dt. Okay. All right, so the whole point of this question is to show you that differential equations and integral calculus is the exact same thing. What we have written here can be rewritten into a differential equation, and they represent the same kind of thing. So there's one other thing I want to show you guys after this, just to, again, show you the comparison between differential equations and integration. All right, so just to do this, what we're going to do is that if we want this to be a differential equation, we're going to differentiate both sides. When you differentiate the left-hand side with respect to x, of course, you're just going to get the derivative y prime. You could also write that as dy dx. When you differentiate the right-hand side, -1 just goes to 0. Plus, then we're going to take the derivative of this integral that we have written up top here. Whenever you differentiate an integral, it's that fundamental theorem of calculus that I hope you guys remember. It just kind of cancels out, but it cancels out in a special way. So what's going to happen is the 1 down here is going to basically do nothing, but we're just going to substitute in x for this dummy variable t. So we still have the y prime on the left. The 0 goes away. The derivative of that integral is just going to be x minus y of x, or you can just think of that as x minus y. All right, now we're not quite done, right? Because we were also asked to find the initial conditions, and we can find the initial conditions by just plugging what we think should be the initial condition back into the equation. What we think should be the initial condition, and what's always going to be the case, is this lower limit here. If I do substitute 1 into that top equation here, so the -1 just comes down, plus, then it's going to be the integral. Remember that we're plugging, the value that we're plugging in, this 1 here, goes into the x's. So the only x is the upper limit here of my integral. So that is going to become a 1. So it's the integral from 1 to 1 of t minus y of t dt. This, I hope, looks familiar to you. Anytime you integrate from a value to the same value, it's just 0, right? Because this is supposed to be areas under the curve, but if there's no horizontal distance, then there is no area. So we get that y of 1 is equal to -1. In other words, the ordered pair 1, -1 is the initial condition. So what that means is that the differential equation y prime is equal to x minus y, where the initial conditions y of 1 is equal to -1, that is the exact same thing as that. Cool. So that's the answer to that homework question. So just that one other thing that I wanted to show you guys just moving forward, something called Maxwell's equations. I hope that you've heard of Maxwell's equations before. If not, it's okay. Maxwell's equations are what not defines, but it explains how electricity and magnetism behave. So these are like the electromagnetic equations. I want to go to Wikipedia here. So these equations are differential equations, but they can also be written as these integral equations, and they're interchangeable. Notice how much nicer they look written as differential equations. Now, I know these symbols probably mean nothing to you, They will once you move on to Calc 3. So these symbols just represent three-dimensional things. It doesn't really matter what, but just know they're derivatives. So this is basically saying that the derivative of the electric field is just P, which I think is the charge, over this constant. This constant has something to do with electricity. The derivative of the magnetic field is always 0. This is something kind of weird. So this is the cross product of the derivative and the electric field. Don't worry what this means. This is the negative derivative of the magnetic field. Basically what this one is saying is that if you have a moving electric field, it creates a magnetic field. What this one is saying is that if you have a moving magnetic field, it creates an electric field. So magnetism and electricity kind of play off of each other based on these differential equations. But these differential equations can be rewritten into integral equations. I know these symbols look crazy. In Calc 3, they'll make more sense. But these are double integrals and triple integrals. This is a closed integral. Again, doesn't really matter. The point is that calculus, integral calculus, and differential equations are really the same exact thing. It's just the way that you kind of notate it and write it all out. All right, let's move on to section 2.